Welcome back to another video on automated surface weather observations. Our last video we talked about ceilings and sky condition and visibility. Now we're going to talk about different types of weather that's measured by ATSC machines. And the first type of weather we're going to talk about is lightning. Lightning can be measured two different ways by an ATSC machine. Either it has a sensor right on the machine or right on the system, or it can measure lightning remotely. Let's talk about the one that's located right on the sensor that's located right on the machine. That's the first system. The second system is a little bit more complicated, and it's called ALDARS, which stands for Automated Lightning Detection and Reporting System. And this came about from the National Lightning Detection Network, which was developed in the 1980s by some scientists in Arizona. And they set up a company, a private company called Global Atmospherics Incorporated, whereby they put sensors all across the United States, measured lightning, and then sold that lightning data to people. They sell it to the government, to golfers, to whoever wants it, actually. Well, Global Atmospherics Incorporated, the company that they set up, was acquired by another meteorological company called Vaisala in 2002. As I mentioned, they set up sensors. They put sensors all across the United States which measure electric field. Each sensor can measure the change in electric field. With many sensors across the United States, each sensor can see a lightning strike and can figure out how close it is to each sensor through triangulation. In other words, if there's a lightning strike in southeastern or North Dakota, 2 or 3 sensors will see that, and it's sent there by satellite. And at Tucson, Arizona, they have computers that can triangulate where the lightning strike is occurring. That information is sent back up to the satellite and then sent to the FAA, local FAA facility near that lightning strike. For example, if there was a lightning strike in North Dakota, then the information would be sent to the Air Route Traffic Control Center in Farmington, Minnesota, and that would be sent to the sensor, the AWAS or ATSC machine in North Dakota, and it would report a thunderstorm, believe it or not. So it's done remotely. It is measured by sensors, and the sensors send their information out. They get the information back, it goes to the FAA, and it ends up on the ATSC machine as reported a thunderstorm. Now this happens in seconds, believe it or not. It seems like it would take a long time, but this happens in seconds. And this is how most AWAS machines operate in Minnesota. This is how they report thunderstorms. The way thunderstorms are reported depends upon the distance that they're measured from the airport or from the ATSC machine. If a thunderstorm is reported from 0 to 5 miles from the ATSC machine, then it'll go into the main body of the METAR as a TS, a thunderstorm. And likewise, from 5 to 10 miles from the airport, it'll be vicinity thunderstorm, which is in the main body of the METAR. But if it's more than 10 miles away, then it's considered distant, and it'll be in the remarks section. And they'll give the direction which the lightning is. So thunderstorm to the northwest, that's 15 miles, will be reported as lightning distant northwest. So these sensors are great because they can pick up thunderstorms well before humans can hear them. And there is a low false alarm ratio, but some of the problems are that you're measuring the change in the electric field strength, and that depends upon the strength of the lightning strike, so there might be some ranging errors. And then also with ALDARS, they have a hard time trying to figure out cloud-to-cloud lightning strikes. Another sensor that measures weather on an ASOS machine is called the LEDWI, which is the Light Emitting Diode Weather Identifier. And what this does is it measures rain and snow, and it measures its intensity also. The way the sensor works is that there is a transmitter and a receiver. The transmitter transmits an infrared light beam, and then there's a photodiode array, which the precipitation, as it falls, it will shadow, and from that, the sensor can determine the type of precipitation. If it's round, then it's rain. If it's jagged, then it's snow. So when it's raining and snowing, that confuses the sensor because it sees rounded and jagged edges, and as a result, it reports unknown precipitation. So the intensity of precipitation, rain specifically, depends upon the power of the return signal, meaning how much of the infrared radiation makes it to the sensor. If it's really light, rain may go unreported. Same thing with snow. Snow sometimes goes unreported, but the visibility determines the intensity of the snow. And with heavy snow, it's reported when visibility is less than 1/4, light snow when visibility is more than 1/2, and moderate is 1/2 to 1/4 mile visibility. And as I mentioned before, light snow, as snow just starts, it may go unreported because it may not see it. And also, snow is not reported when temperatures are greater than 38 degrees Fahrenheit. And you can only report one major type of precipitation at a time. You can't have rain and snow or freezing rain and snow. So this sensor measures precipitation typically sooner than a human does because humans don't continuously monitor. We tend to fall asleep when we're watching the weather. But as I mentioned, some problems are it has a hard time picking up drizzle or light snow, and also it misidentifies ice pellets, snow pellets, and hail. And also, if there are bugs, sometimes the bugs may be reported as another type of precipitation. But whenever you have non-meteorological phenomena in the air, the sensor may have a hard time distinguishing that. Another type of precipitation that is measured is freezing rain. And it's measured by this device. It's called a magnetorestrictive oscillator. And what it is, you can see that silver cone, and on top of that silver cone there's a little rod, and that rod vibrates. And as it vibrates, it is heated, but if there is freezing rain, the precipitation, the freezing rain that freezes on that vibrating rod slows down the vibration of the rod. And as it's coated, it vibrates less and less. Now, when that happens, it measures and records freezing rain. Well, the freezing rain coats the sensor. The sensor will heat up and melt the freezing rain, the ice, off of the sensor, and then it starts vibrating again. So this is what it does. It vibrates, it gets coated, stops vibrating, melts, and vibrates again. And it does this over a period of time. So it can report freezing rain, and when freezing rain is measured, it will issue a special. And freezing rain is reported when the temperature is less than 37 and when there's ice on the sensor. The advantages of the sensor is that it will detect freezing rain a lot sooner than humans. Humans don't monitor the weather very well. Machines do it a lot better. Continues to monitor it 24 hours a day, 7 days a week. So anytime there's an accumulation, it will report the accumulation. But if the snow is very wet, if it's snowing and it's wet, it can compact on that sensor, and the sensor may misidentify it as freezing rain.
The nice thing is that having this capability at the airport, at the ASOS, tells you when there are icing conditions at the airport, and this can be reported in the METAR. If you look at the remarks section of the METARs, you'll see an I group. The I group indicates icing remarks, and it has 4 numbers after the I. The first number tells you that this is the reporting time, how long they are reporting the ice accumulation, and then the 3 numbers after that tell you how much ice was accumulated over that time period, and this amount is to the nearest 100th of an inch. And the ice group is reported hourly, every 3 hours and every 6 hours, if there is freezing rain or icing at the airport.
That's all there is for this video. The next one will talk about obscurations.